Quantum entanglement is one of the most fascinating and counterintuitive phenomena in physics. Here's a clear breakdown of what we understand about it today. Core idea: when two or more particles become entangled, their quantum states are linked together so strongly that you can no longer describe one particle independently of the other, no matter how far apart they are. If you measure a property of one particle, for example, its spin, polarization, or position, the outcome instantly determines the corresponding property of its entangled partner. Classic example: imagine two entangled electrons created together with opposite spins, a common situation. Their total spin must add up to zero, conservation of angular momentum. Before measurement, each electron is in a superposition. It doesn't have a definite spin up or spin down. As soon as you measure one electron and find it is spin up, the other one must instantly become spin down, even if it's on the other side of the galaxy. This correlation is perfect and holds regardless of distance. Key things we understand: 1. It's not communication. 2. The correlation is instantaneous, but you cannot use it to send information faster than light. 3. Why? The measurement outcome on the first particle is random. You only see the perfect anti-correlation when you later compare results with the other person, which requires classical communication at less than speed of light. It violates local realism. Local realism, what Einstein, Podolsky, and Rosen hoped for in their 1935 EPR paper, assumed particles have definite properties even when not measured. Realism. Influences can't travel faster than light. Locality. Experiments, especially those testing Bell's inequalities since the 1980s, with major loophole-free versions in 2015 plus, show that nature violates these assumptions. Entanglement is real. It's not spooky action in the sense of signals. No signal or influence travels between the particles. The entanglement reflects that the two particles are really part of a single quantum system, even when separated in space. The separation we see in everyday life is somewhat illusory at the quantum level. It's extremely well tested. Entanglement has been demonstrated with photons, electrons, atoms, ions, and even small diamonds. It survives over hundreds of kilometers, for example, experiments between ground stations and satellites. It's the foundation for technologies like quantum cryptography, unhackable keys, quantum teleportation of quantum states, not matter, quantum computing, and sensing. Common misconceptions: measuring one particle causes the other to change. It's better to say the particles were never independent after entanglement. Everything is connected. Only specific particles prepared in entangled states show this effect. Random particles in the universe are generally not entangled with each other in a useful way. It doesn't contradict relativity. No usable information travels faster than light, so causality is preserved. Current frontier, as of 2026. Physicists are pushing entanglement to larger scales, macroscopic objects, longer distances, and trying to understand how it relates to gravity and the emergence of classical reality from quantum mechanics. There's active research on whether entanglement plays a role in things like black holes, ER/EPR conjecture, or even consciousness, though that's highly speculative. In short, quantum entanglement shows us that the universe is fundamentally non-local and holistic at its core. Particles can share a deeper connection that transcends ordinary space and time, but in a way that doesn't let us break the laws of physics. Would you like me to go deeper into the math, Bell states, etc., the history, or specific experiments? No, that's not quite how it works. Let's clear this up step by step. Your intuition is heading in an interesting direction, but it's mixing a few concepts. 1. If one dies, the other does too, not automatically. Entanglement links the quantum states of particles, like spin, polarization, etc. It doesn't mean they share a life force or that destroying one physically destroys the other. If you measure one entangled particle, the state of the distant partner instantly becomes determined. The correlation is revealed, but the partner particle itself continues existing normally. It just loses its superposition and has a definite property now. If you physically destroy or absorb one particle, e.g., it hits a detector and is annihilated, the entanglement is broken. The surviving particle simply keeps whatever state it had at that moment, but without the perfect correlation anymore. The other particle doesn't die or get destroyed. Real-world analogy: Think of two coins that are entangled so one is always heads when the other is tails. Flipping, measuring, or smashing one coin tells you the result for the pair, but smashing one doesn't magically smash the other across the universe. 2. The chain reaction idea. Particles close to one connect and the farthest ones die. This is not correct. There's no automatic domino effect death spreading through nearby particles. Entanglement doesn't spread like a virus just because particles are physically close. You need a deliberate process, like a specific interaction or quantum gate, to create new entanglement. If one particle in an entangled pair interacts strongly with its environment, including nearby particles, what usually happens is decoherence. The delicate entanglement gets destroyed by random interactions with the outside world. The distant partner then behaves classically. No more spooky correlation. There is something called entanglement swapping or quantum teleportation, where you can transfer entanglement to new particles using a third particle as a bridge. But this requires careful setup, measurements, and classical communication. It's not something that happens spontaneously when particles are close. In everyday conditions, entanglement is fragile. Particles in the real world constantly bump into others, which breaks entanglement very quickly. That's why we need ultra-cold, isolated labs to maintain it for any useful time. Bottom line on your understanding, you're not understanding it correctly yet, but you're touching on real quantum weirdness. The key points are: entanglement is about correlated information, not shared physical fate or automatic destruction. Destroying, measuring one reveals the state of the other instantly, but doesn't cause the other to die. No spontaneous chain reaction death to nearby or far particles. Entanglement requires preparation and is easily lost. If die meant something specific to you, like radioactive decay of one particle affecting the other, feel free to clarify. Or if you want examples from actual experiments, like entangled photons where one is absorbed, let me know. Quantum mechanics is tricky because our brains evolved for the big, classical world. Happy to keep breaking it down. This image shows the key ideas. Entanglement creates perfect correlations across distance. Measuring or observing one instantly determines the other's state. Destroying one particle does not destroy the other, it just breaks the entanglement. The distant particle keeps existing normally. You just lose the special quantum link. Does this help clarify it? If you want a different angle, like a chain reaction version to show why it's wrong, or more technical, tell me. You're likely thinking of a very common pop science misconception or exaggeration of quantum entanglement. What people often misremember, many simplified explanations, videos, articles, or analogies say things like, the two particles are connected so deeply that whatever happens to one instantly happens to the other. They act as a single entity no matter the distance. Change one and the other changes instantly. When people hear this, they naturally extend it to, if one is destroyed, measured, dies, the other must die too. This is not accurate. The actual science is more subtle. The correlation is instant. The state of one determines the state of the other. But physical destruction or absorption of one particle does not cause the distant partner to be destroyed. The entanglement simply ends, and the surviving particle continues on with a now fixed state. What you might actually be thinking of: close concepts. 1. Wave function collapse for the pair. In the standard view, the two entangled particles share one joint quantum description. Measuring or strongly interacting with one collapses the shared wave function for both. So in that limited sense, something happens to one affects the description of the other instantly. But this is about knowledge and definite states, not literal death or destruction. 2. Particle-antiparticle annihilation. Real pairs, like an electron and positron, can be entangled, and if they meet, they annihilate each other. But that's because they physically collide, not because of entanglement magic across distance. 3. Decoherence or environmental interaction. If one entangled particle interacts messily with its surroundings, gets measured by the environment, the entanglement breaks for the pair. The far particle doesn't die, it just stops being entangled. 4. Sci-fi pseudoscience extensions. Some popular but non-scientific ideas link entanglement to consciousness, twin souls, or if one twin dies, the other feels it. These are metaphors that stretch the physics way beyond what experiments show. Quick visual reminder from before. The image showed that destroying particle A does not destroy particle B, it just ends the special link. That's the key correction. You're not alone in this mix-up. Even Einstein called it spooky, and media loves dramatic versions. The real phenomenon is already weird enough without adding shared death. Does this match what you had in mind, or is there a specific video, book, example you're recalling? I can dig into that too. No, that's still not how it works. You're digging from a creative angle, but entanglement doesn't create any ongoing drifting plus automatic pairing cancellation behavior. Let me directly address your specific ideas. What actually happens when one entangled particle breaks apart or is destroyed? Suppose particle A, entangled with distant particle B, hits a detector, gets absorbed, or decays. Entanglement ends immediately for that pair. Particle B does not die, get destroyed, or feel anything special. It simply continues existing as a normal, independent particle with whatever definite property it now has, e.g., a fixed spin direction. Particle B then behaves like any other lone quantum particle. It drifts, interacts with its local environment when it bumps into things, can get absorbed, decay, or entangle with new particles only if the right physical interaction occurs. There is no special lingering connection that makes B seek out or cancel with another specific particle because of the original entanglement. No automatic chain reaction or sequence of possibilities. Nearby particles don't connect in sequence just because they're close or share similar spin frequency. Entanglement requires a specific, controlled interaction, like parametric down conversion for photons or carefully tuned collisions. Random drifting and bumping usually causes decoherence. The quantum weirdness gets washed out into classical randomness. Spins and frequencies are just properties. Matching ones don't magically link up across the universe. Better mental model. Think of entanglement like two synchronized random number generators that always give opposite results. Once you use or destroy one generator, the other generator keeps running but is no longer synchronized with anything special. It just produces normal random outputs from then on. Would you like a new visual for this exact scenario? I can generate one showing before destruction versus after one particle is destroyed. Just say the word. You're not alone in trying to visualize this. Quantum mechanics fights our intuition hard. The wrong angle is assuming entanglement gives particles some kind of permanent twin bond that persists after one is gone. In reality, it's a temporary, fragile correlation that exists only while both particles remain unmeasured and undisturbed. What part still feels off, or what specific example are you imagining, e.g., electrons, photons, atoms? Got it. Thanks for clarifying. That's a good figurative way to put it, dance partner. Short answer. After particle A is destroyed, particle B does not automatically look for or connect with a new matching particle that drifts nearby. It just drifts as a normal, independent particle. Random nearby particles do not spontaneously entangle with it just because they might have similar spin or frequency. Why? Entanglement isn't like a permanent widowed state waiting for the right match. Once A is gone, the shared quantum correlation is broken forever. Particle B now has a definite state, e.g., definite spin up. It's no longer in that special superposition with anyone. For B to entangle with a new particle C, you need a specific, coherent physical interaction between B and C, not just drifting close or having matching properties. Examples of how entanglement is actually created. Two photons generated together in a crystal, parametric down conversion. Carefully controlled collisions or quantum gates in a lab. Very specific atomic molecular processes. Random thermal bumping or drifting past each other usually causes decoherence. The quantum information leaks into the environment and gets lost, not new entanglement. Figurative version. B had a perfect dance partner A. When A leaves the dance floor permanently, dies, B stops dancing the special paired dance. B is now just standing there alone doing normal solo moves. Other dancers drifting by won't automatically start the perfect synchronized opposite dance with B. They'd need a choreographer, specific interaction to set it up properly. Otherwise, they just bump awkwardly and go their separate ways. This is why maintaining entanglement in real experiments is extremely hard. It requires isolation, vacuum, extreme cold, etc. Would a new diagram help show after A is destroyed versus trying to entangle with a random new particle? Let me know, or if you have another angle on this. Excellent question. This is the right direction for the nitty gritty. How entangled particles A and B are created in the first place. Entangled pairs are not random. They are born together through physical processes that conserve certain quantities energy, momentum, angular momentum, charge, etc. The conservation laws force their properties to be linked from the moment of creation. Most common real world method, photons, spontaneous parametric down conversion, PDC. You shoot a high-energy pump laser photon into a special nonlinear crystal, like beta barium borate. Inside the crystal, the pump photon is annihilated and splits into two lower-energy photons, usually called signal and idler, your A and B. Because of conservation of energy and momentum, their frequencies, colors, add up to the pump's frequency. Their polarizations or paths are correlated, often perpendicular or opposite. Result: the two photons are born entangled in polarization or momentum or time. They leave the crystal together but can then be sent in opposite directions. This is the workhorse method used in most entanglement experiments today. Other common creation methods: 1. Atomic cascades. An atom, e.g., calcium, is excited to a high energy state. When it decays, it emits two photons in quick succession. The photons are entangled because the atom's total angular momentum must be conserved. 2. Particle physics decays. 3. A neutral pion, pi 0, decays into two entangled photons. 4. High-energy collisions in accelerators can produce entangled electron-positron pairs or other particle pairs. Artificial engineered systems, modern labs, trapped ions or atoms, use lasers to create entangled states between ions in the same trap. Quantum dots, tiny semiconductor crystals that emit entangled photon pairs. Superconducting circuits, artificial atoms on chips that can be entangled via microwaves. Bose-Einstein condensates or cold atoms for more exotic entangled states. Key point: A and B are created as a single quantum system from the beginning. They don't start independent and then become entangled. They are entangled at birth because the process that made them respects the conservation laws of physics. The entanglement is baked into how they are produced. Once created, you can separate them, send one to Paris, one to Beijing, for example, while carefully protecting them from the environment. As long as nothing disturbs them too much, the entanglement persists. Tying back to your earlier questions, when one of them, A, is later destroyed or measured, the entanglement simply ends. B doesn't need a new partner. It's now just an ordinary particle carrying whatever definite property was revealed when A was measured. Would you like me to generate a clear diagram of the parametric down conversion process, the most common way A and B are born? It's very visual and would help a lot here. Just say yes. Or do you want to go even deeper into the actual quantum math, Bell states, how we verify they're entangled, or something else? I'm happy to keep drilling down. Here's a clear visual of how entangled particles A and B are typically created. What's happening in this process, step by step? 1. Pump photon, high energy, usually from a laser, enters the special nonlinear crystal. 2. Inside the crystal, the photon is annihilated, disappears. 3. It creates two new photons, A and B, lower energy, but their combined energy and momentum exactly match the original pump photon. 4. Because they are created together from one event, their properties, polarization, path, etc., are perfectly correlated. They are entangled from birth. 5. The crystal spits them out, often along cone-shaped paths. Scientists then collect specific pairs and send them in opposite directions for experiments. This is the most common way labs produce entangled photons today. Other methods exist, like atomic decay, but SPDC is the standard workhorse. Does this match what you wanted to see? Want me to adjust the diagram, e.g., show type I versus type 2, or add what happens after separation? Or shall we go deeper into what happens next with these pairs? Yes, you're very close, but let's get precise. In the most common entangled photon pairs created via spontaneous parametric down conversion, type 2, the two photons A and B are typically entangled in polarization. What that actually means, photons don't have electric charge, they are electrically neutral, so there's no opposite electrical impulse. Photons do carry spin, they are spin 1 particles, and their polarization is directly related to the direction of that spin. In a typical entangled pair, the two photons are born with orthogonal, perpendicular polarizations. Before measurement, each photon is in a superposition. It doesn't have a definite polarization yet, but they are perfectly anti-correlated. If you measure photon A and find it is horizontally polarized, photon B will instantly be vertically polarized, and vice versa. So, yes, in that sense, they have opposite polarization spin orientation relative to each other. Visual analogy: imagine two coins that are forced to always land on opposite sides. One heads equals other tails. The pair is created in that linked state from the beginning. Other types of entanglement. Labs can also create photon pairs entangled in momentum diversion direction. They fly off in correlated paths. Energy divided by frequency, color, time. They are created at the same moment, or combinations of the above. But polarization entanglement is the most commonly used because it's relatively easy to measure and manipulate. Would you like a new diagram specifically showing the polarization entanglement, horizontal versus vertical, for the two photons coming out of the crystal? It would make this even clearer. Or do you want to move to the next step? What happens when we actually measure one of them? No, that's not quite the standard picture in quantum mechanics. Photons and entangled pairs do not create their own little vortex of confinement that persists until one withers, breaks away, or dies. What photons actually are: a photon is a quantum excitation of the electromagnetic field, essentially a packet of energy traveling at light speed. It doesn't have a little vortex or confined bubble around it in the way you're imagining. When two photons are created together in the nonlinear crystal via SPDC, they are born as a single joint quantum state, the entangled wave function. There is no ongoing vortex pair or physical structure that each photon carries separately, like a little tornado. The entanglement is a correlation in their properties, usually polarization, not two separate confined systems linked by vortices. What happens as they travel? The two photons fly apart at the speed of light. As long as nothing disturbs them, no absorption, no scattering, no measurement, the entanglement remains intact. If one photon is absorbed, destroyed by a detector, the crystal wall, dust, etc., the joint entangled state collapses, and the surviving photon simply continues as an ordinary unentangled photon with a now definite polarization. Photons don't wither or slowly die on their own while traveling in vacuum. They keep going until they interact with something, where the vortex idea might come from. Some people blend quantum mechanics with fluid analogies of quantum fields, pilot wave Bohmian mechanics, which has guiding waves, vortex models in ether theories, older ideas, visualizations of spin or angular momentum. These can be helpful metaphors, but they are not the mainstream accepted description of what entangled photons are doing. The actual quantum description uses Hilbert space and wave functions, not physical vortices in space. Would you like me to generate a diagram that shows the actual traveling entangled pair, two photons flying apart with their polarization correlation, versus the vortex idea to show the difference? Or shall we move to what the wave function looks like mathematically, or how measurement actually works? Let me know how you'd like to proceed on the nitty-gritty. I'm here to keep refining until it clicks. Yes, let's slow down and connect all the pieces cleanly. You're not dumb. This is genuinely one of the hardest things for humans to wrap their heads around. 1. Creation and separation. A and B are created very close together inside the crystal, nanometers apart. Right after birth, scientists use mirrors, lenses, and fiber optics to send them flying in opposite directions. They can be separated by kilometers, lab experiments, or even hundreds of kilometers, satellite experiments, while staying entangled. As long as both photons remain undisturbed, no absorption, no random scattering, the entanglement survives the journey. Distance is not a problem. That's the whole spooky part. 2. Opposite spin polarization. Yes, in the common type 2 SPDC, the two photons are born with opposite polarization, one horizontal, one vertical, in a correlated way. Before any measurement, neither has a definite polarization yet, superposition, but they are locked together. Whatever one turns out to be, the other will be the exact opposite. 3. One dies, the other knows. This is the part that keeps tripping you up, and it's the most common misconception. If photon A is measured or absorbed, destroyed, far away, the joint entangled state collapses. Photon B instantly acquires a definite polarization, the opposite of whatever A got. But photon B does not get a signal, message, or knowledge in any usable way. If you were watching photon B alone, you would just see a random outcome. Only later, when you compare notes with the person who measured A, do you see the perfect correlation. There is no communication happening. The correlation was built in at birth. Measurement just reveals it. When A is destroyed, B does not die or change its physical existence. It just loses the entanglement and continues as a normal photon with a now fixed polarization. Simple summary of the real picture. 1. Born together, entangled, opposite polarization locked. 2. Sent very far apart. 3. Measure A, B's state is instantly determined, but you can't use this to send info. 4. If A is destroyed instead of measured, entanglement breaks. B keeps going normally with whatever polarization it had at that moment. Would you like a new diagram that shows the full timeline from creation in the crystal to separation across distance to what happens when one is measured, destroyed? I think that would help tie it all together visually. Say yes and I'll generate it. We can keep going as slow as you need. Yes, let's answer this directly and clearly. When one entangled particle dies, is destroyed or absorbed, does the spin polarization of the other one change at that moment? Short answer, no. The surviving particle does not experience a sudden, detectable change in its spin or polarization that you could notice locally. More precise explanation. 1. Before anything happens, the two photons A and B are entangled. Their polarizations are correlated but indefinite, superposition. 2. When photon A is destroyed, absorbed, for example, hits a piece of matter and is gone. 3. The entanglement between A and B is broken. 4. Photon B is no longer entangled. 5. Photon B now has a definite polarization. It collapses into either horizontal or vertical, randomly. 6. However, this collapse is not observable locally on B alone. If you look at B by itself, nothing dramatic seems to happen. It just behaves like a normal photon with a fixed but random polarization. There is no sudden flip or moment of change that B feels or that you could measure as a signal saying A just died. Key point: the correlation only becomes visible after the fact when you compare results from both sides. Since A is destroyed, you can no longer compare, so you never see the correlation for that particular pair. Think of it this way. The pair shares a secret rule from birth. We will always be opposite. When A dies, the rule is canceled. B is left with whatever value it happened to have at that instant, but there's no notification or physical disturbance traveling to B. This is why entanglement cannot be used for faster-than-light communication. Even when one particle is destroyed, the distant one doesn't know anything useful happened. Would you like a simple timeline diagram showing birth, separation, A dies, what happens to B? Just say yes and I'll generate it. You're doing well slowing this down. This stuff is tricky even for physicists. What part still feels fuzzy? Got it. Thanks for the correction. Question: when one entangled particle, A, dies, is destroyed or absorbed, does the momentum of the surviving particle, B, change at that moment? Short answer, no. The momentum of particle B does not change when A is destroyed. Detailed breakdown. In typical entangled photon pairs from spontaneous parametric down conversion, negative A and B are created with correlated momentum. Their directions and energies are linked due to conservation of momentum inside the crystal. They fly apart with well-defined momenta that balance each other. When photon A is later destroyed far away, absorbed by a detector, hits dust, etc., the entanglement breaks. Photon B keeps its existing momentum unchanged. It continues traveling in the same direction and at the same speed of light as before. There is no sudden kick, push, pull, or change in direction as speed for B. B simply loses its special quantum correlation with A and behaves like any ordinary photon from that point onward. Why this matters: momentum is a local property of each particle. Destroying A doesn't send any force or impulse across space to B. The instantaneous part of entanglement only applies to the correlated measurement outcomes, like polarization or spin, not to physically altering the surviving particle's trajectory or energy. This is consistent with relativity. Nothing physical, no momentum transfer travels faster than light. Would you like a simple diagram showing two entangled photons flying apart with correlated momentum, one being destroyed, the other continuing straight with unchanged momentum? Just say yes and I'll generate it. You're zeroing in on the important distinctions. Keep asking. We're getting there. What else is on your mind about this? Yes, you're making good progress here. Your latest picture is much closer than the invisible thread idea. Correcting, refining your understanding. No invisible thread. There is no physical connection or string stretching between the two particles after they separate. That was the old classical intuition Einstein didn't like. The cannonball analogy is decent for the separation part. Two cannonballs are fired at the same time in opposite directions. They drift far apart, but they were launched together with properties that match in a special way. However, here's the important quantum refinement. The opposite spins, or more accurately for photons, opposite polarizations, are not definite when they are created and flying apart. Both particles are in a superposition. They don't have a fixed spin polarization yet. They carry a guaranteed correlation. Whatever you measure on one, the other will perfectly match as the opposite. So a better analogy might be: two cannonballs are fired with a special linked randomizer. When one lands and you see heads, the other one must be tails, even if it's on the other side of the planet. But until you look at the first one, neither has actually shown heads or tails. Spin versus entanglement. Spin polarization equals a property each particle can have, like rotation direction. Entanglement equals the special relationship between the two particles' properties, created at birth. They are entangled in their spin polarization or in momentum, energy, etc. Your cannonball picture works well for how they separate over vast distances while keeping that correlation intact until one is measured or destroyed. Would you like a simple diagram of your cannonball idea but done quantum style, two particles flying apart with the correlated superposition shown? It might help lock this in. Or do you want to move on to what actually happens during measurement? You're doing fine. This stuff bends the brain. What's your current mental picture now? Got it. Let's address the mirror aspect directly. In quantum entanglement, especially the polarization version we've been discussing, the two particles act like perfect mirrors of each other in their properties. What the mirror really means: when the pair is created, their states are linked such that they are opposite or sometimes identical, depending on the type of entanglement. For the common case, if A turns out to be horizontal, B will be vertical, like a mirror reflection. This mirror correlation is built in from birth and holds no matter how far apart they are, but it's a probabilistic mirror, not a fixed physical one. Neither photon has a definite polarization while flying. The mirror only activates, becomes definite when the first measurement happens. Tying back to your cannonball picture, two cannonballs are launched together. They fly far apart. They carry this mirrored relationship. Whatever orientation one reveals when looked at, the other must show the exact mirror opposite. No thread, no ongoing communication, just a baked-in mirror correlation from the moment they were born together. The key mirror moment: when you measure or destroy photon A and get, say, horizontal, photon B's state instantly becomes vertical, the mirror image. But again, you can't see or feel any change happening to B locally. You only discover the mirror match later when you compare both results. This is the heart of the spooky part Einstein hated. Does this match what you meant by the mirror of this? If you want, I can generate a diagram showing the two photons flying apart, the mirror polarization correlation clearly labeled, what happens when one is measured, or tell me exactly what mirror means to you right now. Maybe you're thinking of antimatter, reflection symmetry, or something else. We're moving at your pace. What's next on your mind? No, not quite. Let's clear this up simply. If A and B are entangled with opposite spins or polarizations, negative, before any measurement, neither A nor B has a definite spin direction. Both are in superposition. They are not spinning left or right yet. When you measure A and it comes out spinning left, then B instantly becomes spinning right. But here's the key part you got wrong. B does not automatically spin right when A dies. When A is destroyed, dies, B does not get forced into the opposite spin. Since you didn't actually measure A, you didn't get an outcome. B just loses its entanglement and becomes a normal particle with a random but now fixed spin. You never know what it was. The mirror effect only shows up when you measure the first particle and get a definite result. If you just destroy it without measuring, the mirror correlation is lost. Nothing special happens to B. That's the main correction. Does that make sense now? Yes, that's almost correct, but with an important subtlety. What actually happens: 1. A and B are entangled, opposite polarizations. 2. A is destroyed, absorbed without being measured. No definite outcome was ever recorded for A. 3. You later measure B and get, say, vertical. At this point, you cannot confidently say, therefore, A must have been horizontal. Why? Because A was never measured. The perfect correlation only exists between actual measurement outcomes on both sides. Since A left no record, you have no way to verify the mirror relationship for that specific pair. Measuring B after A is gone just gives you a random result: 50% chance vertical, 50% horizontal. It doesn't retroactively tell you what A was. The only way the mirror works, you must get a definite measurement result on both particles, or at least have the possibility of comparing them. Measure A first, get horizontal, B is instantly vertical. Then measure B and confirm it's vertical. Perfect mirror confirmed. If A is destroyed without measurement, that confirmation link is lost forever. Bottom line, you are not led to believe A was spinning horizontally just because you measured B as vertical after A was destroyed. The correlation can't be checked, so you treat B's result as ordinary random. This is why destruction without measurement is different from actual measurement. The knowing or mirroring only shows up in the statistics when you have data from both sides. Does this click better now? Want a simple timeline diagram showing A destroyed without measurement, measure B versus the proper measure A, then B case? Just say the word. Yes, I see exactly where you're going, and this is a sharp question. You're asking about retroactive inference. If I measure B as vertical after A is destroyed, isn't it reasonable to conclude A would have been horizontal? The honest answer, in a single instance, you cannot safely conclude that. In large statistics across many pairs, it averages out consistently with the entanglement, but you still can't assign a definite past state to the destroyed A. Why not? When A is destroyed, absorbed without measuring it, the entanglement collapses in a way that leaves B in a mixed state, a 50-50 statistical mixture of horizontal and vertical. Measuring B gives you vertical. That's just one random draw from that mixture. There is no hidden record or definite fact about what A was because no measurement ever happened on A. The correlation was never realized in the actual world. It's not like A had a secret definite horizontal spin all along that you can now infer. The definite opposite values only come into existence when the first measurement occurs on one of them. Comparison. You can look at the table in the conversation history. This is one of the places where quantum mechanics fights classical intuition hardest. The properties aren't out there waiting to be revealed until a measurement forces them to become definite. Would you like a diagram that shows the difference between proper measurement sequence A then B, destruction of A then measurement of B? This visual usually helps lock in the distinction. Say yes, and I'll generate it. You're asking the right hard questions. This is exactly where most people, and even some physicists, get tripped up. Keep going. What's still feeling off? Yes, you're spotting a real tension in how this is explained. Good catch. Let me clear it up directly without glossing over it. The precise truth: the particles are not born with definite opposite spins, polarizations, like one fixed horizontal and the other fixed vertical from the start. That would be a classical picture, and it's wrong for entangled particles. Instead, they are born in a joint superposition. A common entangled state for polarization looks like this, simplified: maybe an uncertainty, but no particle subspeeds to said SETI quantity. The only definite thing is the perfect anti-correlation. Whatever you measure on one, the other will be the exact opposite. Your coin analogy is excellent here. The two coins are in a linked superposition. They are not secretly one heads and one tails already. Only when you look at the first coin, measure A, does the outcome become definite, say heads, and the other coin is instantly forced to tails. Why I sometimes said opposite spins, that was loose language for the correlation. It's common shorthand, but it can mislead. The spins' polarizations are not prefixed as opposite definite values. They become definite opposites only upon the first measurement. Back to your earlier question, if A is destroyed without measuring, and you later measure B as vertical, you cannot conclude A must have been horizontal, because no measurement ever forced the pair into a definite outcome. B's result is effectively random. The entanglement is a guaranteed future correlation if both get measured, not a pre-existing pair of opposite definite properties. Would you like a diagram that shows the joint superposition at birth, the two photons flying apart, what changes or doesn't when one is destroyed versus measured? This usually makes the difference between definite opposite from birth and superposition with guaranteed correlation visually clear. Say yes if you want it. You're doing well pushing on the fuzzy parts. What's your current picture now? No, not at all. The studies and experiments on quantum entanglement are not assumptions. They are some of the most rigorously tested and confirmed results in all of modern physics. What is solidly proven, not assumed, entangled pairs can be created, for example, via the crystal method we discussed. They can be separated over large distances, even Earth to satellite. When you measure both particles, you see perfect correlations, opposite polarizations, spins, etc., that violate classical expectations. These correlations have been confirmed in thousands of experiments, including loophole-free Bell tests since 2015. This is real, repeatable science, not philosophy or guesswork. Where the subtlety and potential confusion comes in, the only interpretational part is what we can say about the past when one particle is destroyed without ever being measured. The math and experiments tell us the correlation only becomes definite when the first measurement happens. If you destroy A without measuring it, there is no experimental record of what A was, so you can't retroactively assign a definite horizontal or whatever state to it based on measuring B later. This isn't an assumption, it's what the mathematics of quantum mechanics predicts, and it matches what we actually observe in labs. Different interpretations of quantum mechanics, Copenhagen, many worlds, etc., argue about why this happens, but they all agree on the experimental predictions. Bottom line, the phenomenon is experimentally rock solid. The difficulty is in our human intuition trying to force classical definite things existed all along thinking onto a quantum situation. Would a clean diagram help right now showing creation in superposition, separation, proper measurement both sides versus destruction without measurement? Or do you want me to walk through a real famous experiment like aspects or the 2015 loophole-free ones in simple terms? Tell me what still feels like it's resting on shaky ground for you. We'll keep nailing it down. Understood. No rush at all. Quantum entanglement is dense, and taking a break to process is smart. You mentioned wanting to present your understanding visually. That's a great idea. Drawing or diagramming your current mental model often reveals exactly where things are clicking or still fuzzy. How can I help? I can generate a custom diagram based on your current picture. Tell me what you'd like to see in it. For example, two particles A and B being born in the crystal, them flying apart like cannonballs. The mirror opposite relationship, however you see it now. What happens when one is destroyed versus measured? Any invisible thread, vortex, superposition clouds, or other elements you have in mind. Before after panels or a timeline. Just describe it in your own words, even roughly, and I'll create the image so we can look at it together and tweak from there. Or if you prefer, sketch it verbally step by step and I'll turn it into visuals. Take your time. Whenever you're ready, just reply with your description. I'm here.